Respiratory physiology of lung volumes and capacities includes 4 volumes and 4 capacities. A capacity is the sum of 2 or more physiologic volumes. Tidal volume is the air that moves into the lung with each quiet inspiration, which is 6 to 8 milliliters per kilogram, typically around 500 milliliters. Inspiratory reserve volume is the air that can still be breathed in after normal inspiration. Expiratory reserve volume is the air that can still be breathed out after normal expiration. Residual volume is the air left in the lung after maximal expiration, and residual volume, along with any lung capacity that includes residual volume, cannot be measured by spirometry. Inspiratory capacity is defined as inspiratory reserve volume plus tidal volume, which is the air that can be breathed in after normal exhalation. Functional residual capacity is residual volume plus expiratory reserve volume, representing the volume of gas in the lungs after normal expiration, where the outward pulling force of the chest wall is balanced with the inward collapsing force of the lungs. Vital capacity is inspiratory reserve volume plus tidal volume plus expiratory reserve volume, which is the maximum volume of gas that can be expired after a maximal inspiration. Total lung capacity is inspiratory reserve volume plus tidal volume plus expiratory reserve volume plus residual volume, or vital capacity plus residual volume, which is the volume of gas present in the lungs after a maximal inspiration. The work of breathing refers to the energy expended or oxygen consumed by respiratory muscles to produce the ventilation needed to meet the body's metabolic demand. It is a combination of flow-resistive and elastic work, meaning work equals force times distance, or pressure times volume, and it is required to overcome both elastic recoil and airway resistance. The work of breathing is minimized by optimizing respiratory rate and tidal volume. In restrictive diseases, the work to overcome elastic recoil resistance is achieved with higher respiratory rate and lower tidal volume. In obstructive diseases, the work to overcome airway resistance is achieved with lower respiratory rate and higher tidal volume. Physiologic dead space equals tidal volume multiplied by arterial partial pressure of carbon dioxide minus expired air partial pressure of carbon dioxide divided by arterial partial pressure of carbon dioxide. Or VD equals VT multiplied by PaCO2 minus PeCO2 divided by PaCO2. Physiologic dead space is the anatomic dead space of the conducting airways plus alveolar dead space. The apex of the healthy lung is the largest contributor of alveolar dead space. VD represents the volume of inspired air that does not take part in gas exchange. PaCO2 is the arterial partial pressure of carbon dioxide, and PeCO2 is the expired air partial pressure of carbon dioxide. In normal lungs, physiologic dead space is approximately equivalent to anatomic dead space. Physiologic dead space may be greater than anatomic dead space in lung diseases with ventilation perfusion mismatch.